What if everything we think we know about distant worlds is only half the story? Tonight on ASMR Dreams, we're diving into one of the most mysterious frontiers of modern science: exoplanets, worlds orbiting other stars, planets that burn, freeze, drift, collide, and sometimes look almost familiar. But here's the twist. What if we've never actually seen them the way we imagine? But what if most of it is inference? Models layered upon light that has traveled for years across empty space. How much do we truly know? And how much are we carefully reconstructing from shadows? On ASMR Dreams, we don't chase easy answers. Are exoplanets really other Earths? Stay with me, because by the end of this journey, you may see the night sky differently, not as a collection of distant lights, but as a vast archive of hidden worlds, waiting to be interpreted. Welcome to ASMR Dreams. In modern astronomy, the term exoplanet refers to a planet that orbits a star beyond our solar system. The definition itself sounds simple, almost quiet, almost ordinary. And yet behind this calm phrase lies one of the most profound shifts in scientific understanding in recent decades. A change in how we see planetary systems and how we understand the place of our own solar system among them. For a long time, exoplanets were not objects of confirmed knowledge. They belonged to speculation, to equations written on blackboards, and to silent assumptions about how stars are born. Planets were often considered rare, perhaps even unique, something that happened under very specific conditions during the formation of our sun. Observational astronomy did not allow scientists to directly detect planets around other stars. So for many years, other planetary systems were possible, but unproven. Exoplanets lived in the realm of hypothesis rather than observation. The situation began to change as observational techniques improved. Measurements became more precise. Data analysis became more refined. Astronomers learned to detect extremely subtle effects, tiny shifts in starlight, delicate changes in motion, signals so faint that they could easily be mistaken for noise. Importantly, these effects do not usually appear as direct images of the planets themselves. Instead, they reveal themselves indirectly, through the influence a planet exerts on its parent star. A small gravitational pull, a slight dimming of light, a periodic wobble. This indirect nature of detection shaped the entire field of exoplanet research. From the very beginning, discoveries showed that planetary diversity is far greater than previously imagined. Many detected exoplanets have no true analog in our solar system, not in mass, not in orbital configuration, not in physical conditions. Some are enormous gas giants orbiting extremely close to their stars. This expanded our understanding of what planetary systems can be. Exoplanets are no longer viewed as rare exceptions. Modern science considers planet formation to be a natural byproduct of star formation itself. When a star is born from a collapsing cloud of gas and dust, a disk of material forms around it. Within that disk, particles collide, merge, and slowly build larger bodies. Planets are not anomalies. They are consequences. However, the exact characteristics of any planetary system depend on many factors: the mass of the star, the chemical composition of the surrounding material, and the complex dynamics of the early stages of evolution. Exoplanets provide the observational material needed to test these theoretical ideas. The transition from theoretical possibility to observational confirmation carried important methodological consequences. Astronomy had to develop ways of interpreting signals that are extremely weak compared to the overwhelming brightness of stars. This required long-term monitoring programs. In exoplanet research, the distinction between detecting an object and understanding its properties is especially clear. It should also be noted that exoplanets are not studied in isolation. They exist within specific stellar systems. The properties of the host star determine orbital parameters, temperature conditions, and long-term dynamical stability. For this reason, Exoplanet astronomy is inherently interdisciplinary. It brings together stellar physics, planetary science, gravitational dynamics, and studies of the interstellar medium. Some are massive enough to approach the lower boundary of stars. Others are comparable in size to Earth. The boundary between planets and other objects is not always sharply defined. It is often operational, a tool of classification rather than a strict natural division. This reflects a broader principle in astronomy. Classifications help us think, but nature itself does not always obey neat categories. Exoplanets have also transformed our view of orbital architecture. Before their discovery, the solar system was often assumed to represent a typical planetary arrangement. Observations of other systems showed that this assumption may not be correct. There exist systems with extremely compact orbits. Systems where massive planets orbit very close to their stars. Configurations that are difficult to explain using earlier formation models. These findings forced scientists to reconsider ideas about planetary migration and long-term dynamical evolution. An important aspect of exoplanet research is that it operates under conditions of incomplete information. In most cases, only certain parameters, such as mass, radius, or orbital period, are known. Many other properties are inferred indirectly and carry significant uncertainties. Models must be continuously refined. Conclusions must be revisited as new data accumulate. Exoplanet science does not progress as a straight line. It advances gradually, like adjusting a lens until the image becomes clearer. Exoplanets also play a central role in discussions about how common planets are in the universe. Observations indicate that planets occur around a significant fraction of stars. However, estimates depend on detection methods and on which types of planets are considered. Science does not seek a single exact number. It seeks ranges, patterns, statistical trends. This reflects the broader approach to studying complex systems. Although that aspect captures public imagination, the scientific scope is much wider. Exoplanets are physical objects governed by universal laws. Their diversity allows scientists to test those laws under conditions not present in our own solar system. In this sense, each exoplanet is like a natural experiment conducted by the universe itself. A scientific approach requires a clear distinction between confirmed results and hypotheses. The existence of exoplanets is firmly established. However, details of their internal structures, atmospheres, and evolutionary histories often remain under discussion. Different models can explain the same observations with varying degrees of success. This is not a weakness of science. Exoplanets also raise the question of how universal the processes that formed our solar system truly are. The diversity of observed systems suggests that universal mechanisms may manifest differently depending on initial conditions. This makes exoplanets a key element in understanding cosmic diversity and the stability of physical laws. Thus, in modern scientific understanding, exoplanets are not merely planets around other stars. They represent an entire class of objects that has radically expanded our conception of planetary systems. Their study relies on indirect methods, on careful interpretation, on patient accumulation of data. When we look at exoplanets calmly and systematically, they cease to be sensational discoveries. They become what they truly are, natural outcomes of stellar evolution and profound sources of knowledge about the structure of the universe. And even now, as you listen quietly and allow your thoughts to drift among distant stars, it is worth remembering something gentle and beautiful. For most of human history, we did not know whether other worlds existed. Now we do. Somewhere, orbiting distant suns, countless planets move in silent paths, unseen by the naked eye, yet carefully traced by subtle signals in starlight. The discovery of exoplanets remains one of the most demanding challenges in observational astronomy. It requires patience, precision, and humility before the faintest whispers of data. But it also reminds us of something deeply comforting. The universe is not empty. It is full of worlds. They exist in the overwhelming glow of stars that are millions or even billions of times brighter. Against that brilliance, a planet is almost invisible, a quiet shadow beside a radiant flame. For this reason, direct imaging of exoplanets is, in most cases, impossible. The light of the star simply drowns them out. And so, the science of exoplanets has grown primarily through indirect methods, each one based on measuring subtle secondary effects caused by the presence of a planet. One of the most widely used approaches relies on analyzing the motion of a star. A planet and its star form a gravitationally bound system. Both objects orbit a common center of mass. The motion of the star is much smaller than that of the planet, but with sufficient precision, it can be detected. Astronomers measure tiny changes in the star as velocity along the line of sight, slight shifts in its spectrum caused by motion toward or away from us. This periodic wobble is interpreted as evidence of an orbiting companion. From this method, scientists can estimate the planet's mass and the parameters of its orbit. However, the technique is most sensitive to massive planets and to systems whose orientation aligns favorably with our line of sight. Smaller planets, or those in less convenient geometries, may remain hidden. Another major method involves periodic dimming of starlight. If a planet's orbit is aligned so that it passes between its star and the observer, it will temporarily block a small fraction of the star's light. By analyzing these light curves, astronomers can determine the planet's radius and refine orbital parameters. Yet this method applies only to systems with a specific geometric alignment. Most planetary systems are oriented differently, and their planets never transit from our perspective. The geometry of the cosmos determines what we are able to see. Combining different detection methods is crucial for obtaining a more complete understanding. When both the mass and radius of a planet are measured, scientists can estimate its average density. From density, they infer whether the object is predominantly gaseous or contains a substantial fraction of solid material. Still, these conclusions remain generalized. They do not reveal the detailed internal structure of the planet. They offer hints, not blueprints. Other detection techniques exist as well, though they are used more rarely or in specialized circumstances. Some rely on measuring tiny shifts in a star's position on the sky. Others observe the temporary brightening of a distant background star when an intervening object's gravity bends its light. Each method carries its own strengths and limitations related to sensitivity, applicability, and interpretation. Together, they form a toolkit that allows astronomers to probe different kinds of planetary systems. The observed diversity of exoplanets reflects not only the true properties of planetary systems, but also the biases of the methods used to find them. Massive planets in close orbits are easier to detect than small planets on distant paths. Short orbital periods are easier to observe within limited timeframes than long ones. Statistical conclusions must therefore be corrected carefully for observational biases. What we see is shaped by how we look. Observability is also constrained by data quality and by the duration of observational programs. Many planets have orbital periods longer than the time span of our monitoring campaigns. Their presence may go unnoticed or appear only partially. This means that current exoplanet catalogs represent an incomplete sample of the true population. Science acknowledges this incompleteness. It cannot fully eliminate it. Interpreting weak signals presents additional challenges. Variations in stellar brightness or velocity may arise not only from planets, but also from internal stellar processes. Surface activity, pulsations, magnetic phenomena, all can mimic planetary signatures. Distinguishing between these causes requires long-term data collection, additional diagnostic indicators, and careful statistical analysis. Even then, ambiguity may remain. As detection methods improved, measurement precision steadily increased. This allowed the discovery of smaller and less massive planets. Yet greater sensitivity also introduced more borderline cases, signals that hover at the threshold of noise. It is also important to note that detecting a candidate exoplanet does not guarantee immediate confirmation. Scientific practice requires repeated observations and independent verification. Only after passing through these stages is an object included among confirmed exoplanets. This process can take years. It reflects the cautious nature of the scientific method. Observational limits are further influenced by distance. Most detected exoplanets reside in relatively nearby regions of our galaxy, at least by cosmic standards. More distant systems remain difficult to study in detail. Thus, exoplanet astronomy largely explores a local fragment of the Milky Way. Extending conclusions to the entire universe requires additional assumptions. Detection methods continue to evolve. Instruments become more sensitive. Data processing becomes more refined. Yet even with ideal technology, fundamental constraints remain, imposed by geometry and by the physical properties of systems themselves. A complete and exhaustive description of all exoplanetary systems is, in principle, unattainable, and this awareness is important. The methods of detection define both what we know and the boundaries of our knowledge. Exoplanets are studied through indirect effects, statistics, and models, not through direct sensory perception. Recognizing these limitations allows for a calm and balanced understanding of what science truly knows about exoplanets and where uncertainty begins. The first confirmed exoplanets immediately demonstrated that planetary systems can differ dramatically from our own. This led to the reconsideration of assumptions that once seemed almost self-evident. Classifications based solely on familiar solar system examples proved insufficient. One of the most striking discoveries was the existence of massive planets orbiting extremely close to their stars. Such objects have no direct analog in the solar system. Their presence challenged the idea that large planets necessarily form and remain on distant orbits. Current models suggest that some of these planets may have formed farther out and then migrated inward through interactions with surrounding material or with other planets. Alongside massive objects, astronomers have discovered planets with sizes and masses intermediate between Earth and the giant planets, a category absent in our solar system. For a long time, this absence was assumed to be typical. Exoplanet observations revealed that it is more likely a special case. These intermediate planets form a distinct class with diverse properties. Their internal structures and compositions may vary substantially, even when their sizes appear similar. Diversity among exoplanets is expressed not only in mass and radius, but also in density. Planets of identical size can have very different densities, indicating differences in composition. Some contain large fractions of light elements. Others are composed predominantly of heavier materials. Behind each measurement lies complexity. Behind each data point, a world. And as we reflect on these distant planets, revealed only through faint signals and careful inference, we are reminded of something quietly profound. The universe allows for more variety than we once imagined. Worlds of many kinds. Arrangements we did not predict. Structures we are still learning to understand. And in this gentle expansion of knowledge, there is no rush. Only patient observation, careful reasoning, and the steady widening of our cosmic horizon. It cannot uniquely determine what lies beneath the surface. A world with a given mass and radius may conceal a layered interior, a deep ocean of exotic materials, or a compressed rocky core wrapped in volatile gases. The numbers guide us, but they do not fully reveal. Exoplanets also display a wide range of orbital configurations. Some systems contain multiple planets packed into remarkably compact arrangements, orbiting their stars at distances far smaller than Mercury's orbit around the Sun. These tightly spaced configurations require delicate dynamical balance. Their stability implies a complex formation history, one shaped by migration, interaction, and long-term gravitational negotiation. Other systems exhibit highly elongated orbits, In such cases, a planet's distance from its star changes dramatically during a single revolution. These variations raise questions about long-term stability and about the mechanisms that prevent chaotic disruption. Each orbital pattern tells a story, though often only in fragments. Gradually, classification based purely on analogy with the solar system has given way to more functional approaches. Instead of searching for direct counterparts to Earth, Jupiter, or Neptune, orbital characteristics. This parameter-based framework allows observed diversity to be organized without forcing it into familiar shapes. It is important to remember that the diversity we observe is shaped partly by detection limits. Statistical corrections help reduce these distortions, but they cannot remove them entirely. For this reason, conclusions about the typical properties of planets are expressed with caution. Diversity also raises questions about the varied boundaries of the term planet. Some discovered objects lie near the transition between planets and other categories of astronomical bodies. Their classification depends on criteria that are themselves operational and somewhat flexible. Nature does not always divide itself into clear compartments. Scientific categories are tools, not rigid borders. Exoplanetary systems often reveal intricate relationships among planets. Orbital resonances and other dynamical connections indicate that planets evolve together, influencing one another over time. These interactions may have shaped the present architecture of the system. By analyzing such configurations, scientists infer aspects of early evolutionary stages. Yet these inferences remain probabilistic and model-dependent. The diversity of exoplanets also informs discussions about the conditions required for complex systems. Individual parameters may resemble those of Earth, yet the overall context often differs substantially. Similarity in one aspect does not imply equivalence in total conditions. Science avoids simplistic analogies. Each system is treated as a unique combination of factors. Importantly, this diversity does not contradict physical law. On the contrary, it demonstrates how universal laws can produce a wide spectrum of outcomes depending on initial conditions. Exoplanets expand the empirical foundation on which models of planetary formation and evolution are tested. Each newly studied system adds another realization of general principles, another variation within the same cosmic grammar. Our current understanding remains incomplete. Some classes of objects are represented by only a handful of examples. Many parameters carry substantial uncertainties. Classifications will continue to evolve as new data accumulate. Revision is not instability. It is the natural rhythm of scientific growth. Thus, exoplanets have shown that planetary systems may be structured far more diversely than previously assumed. This diversity invites flexibility, careful analysis, and a willingness to release narrow comparisons. Now we turn gently to one of the most intricate and informative areas of exoplanet research, the study of planetary atmospheres. If present, an atmosphere plays a decisive role in shaping a planet's observable properties. It reflects the history of formation, evolution, and interaction with its star. Yet, in the case of exoplanets, we do not observe atmospheres directly. Instead, we detect their influence on starlight. During a planetary transit, a small fraction of stellar light passes through the planet's atmosphere. Certain wavelengths are absorbed more strongly than others, depending on the chemical composition and structure of the gaseous envelope. By analyzing these subtle spectral variations, scientists infer the presence of specific components. These conclusions are probabilistic. The changes in signal are often fractions of a percent, sometimes even smaller. Instrumental noise, stellar activity, observational conditions all may influence the result. Therefore, atmospheric analysis demands rigorous statistical treatment and repeated verification. Even when spectral signatures are identified, they do not provide a complete description. Observed features depend not only on chemical composition, but also on temperature, pressure, cloud distribution, and atmospheric dynamics. Different combinations of these factors can produce similar observational effects. Science often works not with single answers, but with families of plausible models. Exoplanet atmospheres themselves exhibit striking diversity. Some planets possess dense gaseous envelopes. Others have tenuous or unstable atmospheres. In certain cases, particularly for planets close to their stars, intense stellar radiation gradually strips atmospheric gases into space. The rate and mechanisms of atmospheric loss depend on many variables and remain active areas of research. Atmospheres are not necessarily permanent structures. Over time, a planet's gaseous envelope may change significantly. Loss of light elements, shifts in chemical composition, redistribution of energy. These processes can drive transitions between atmospheric states. Such transitions may be gradual, yet they can fundamentally alter the character of a world. Studying the atmospheres of smaller exoplanets presents special challenges. Their influence on starlight is weaker than that of massive planets. Data for these objects are limited and carry larger uncertainties. And yet, these smaller worlds are of profound interest. They extend our understanding into ranges of planetary conditions not represented in the solar system. It is essential to emphasize that an exoplanet's atmosphere is not necessarily analogous to Earth. The presence of particular gases does not automatically imply similar environments. Chemical reactions, photochemical processes, and atmospheric dynamics may differ significantly under other temperatures and pressures. Science approaches atmospheres as physical systems governed by universal laws, but realized under specific conditions. The study of exoplanet atmospheres is closely tied to advances in observational instruments. Each new generation of telescopes refines our sensitivity, allowing ever more delicate measurements. Yet even as technology improves, fundamental uncertainties remain. And that is part of the quiet beauty of this field. We are listening to faint whispers carried across light years. We are reading signatures etched in starlight. We are learning to interpret shadows and subtle shifts, not with haste, but with patience, with care, with the steady calm of science unfolding over time. Improvements in spectral resolution and instrumental stability have gradually expanded the range of accessible atmospheric data. Yet even under the most favorable conditions, a fundamental limitation remains. Exoplanetary atmospheres are not observed directly. They are inferred through their influence on starlight. This means that interpretation will always depend on models and on underlying assumptions. Alternative explanations often exist for observed spectral features. Different models may attribute the same absorption signature to different combinations of temperature, composition, cloud structure, or atmospheric dynamics. In scientific practice, such alternatives are considered in parallel, without premature exclusion. Exoplanet atmospheres also serve as indicators of star-planet interaction. Radiation, stellar wind, magnetic activity, all can significantly affect atmospheric structure. These interactions form complex feedback systems that shape the planet's long-term evolution. However, quantitatively describing these processes is challenging. It requires accounting for numerous parameters, many of which cannot yet be measured directly. It is important to recognize that our knowledge of exoplanet atmospheres remains fragmentary. For most known planets, the atmosphere is either unstudied or described only in broad terms. And yet, even these limited data have already expanded our understanding of the possible states planetary envelopes may assume. They reveal atmosphere not as a static shell, but as a dynamic, evolving component of a planet's identity. Thus, the study of exoplanet atmospheres is an area where observation, modeling, and hypothesis are tightly interwoven. The atmosphere becomes a window through which science attempts to glimpse deeper internal processes and long evolutionary histories. A calm and careful consideration of these findings allows us to appreciate not only what is known, but also the vast territory of uncertainty that remains. Now we turn gently toward another essential dimension of exoplanetary science: orbital dynamics. The orbital architecture of an exoplanetary system is a key to understanding both its present configuration and its past evolution. Observable parameters, orbital periods, eccentricities, mutual inclinations are the result of long processes unfolding since the system's formation. These parameters are not permanently fixed. They evolve under gravitational interactions that may be subtle and gradual, or occasionally dramatic. Planetary systems form within protoplanetary disks, where gas and solid material are unevenly distributed and constantly in motion. In this environment, emerging planetary orbits are not isolated trajectories. They form and change within a medium rich in gas and particles. Interaction between a planet and its surrounding disk leads to exchanges of angular momentum. This process, known as planetary migration, has become a central element of modern models. Migration is considered a plausible explanation for the presence of massive planets on close-in orbits. Interaction with the disk can gradually alter a planet's distance from its star. The speed and direction of this shift depend on planetary mass, disk density, temperature, and other factors. Yet the details remain complex. Many parameters are difficult to measure directly. Migration is therefore viewed not as a universal scenario, but as one of several possible evolutionary pathways. After the gas disk disperses, system dynamics are governed primarily by gravitational interactions among the planets themselves. If the configuration is near equilibrium, these interactions may remain stable for long periods. However, even small perturbations can accumulate over time, leading to significant rearrangements. In some systems, evidence suggests that orbital evolution continued long after the main formation stage had ended. Resonances occur when planetary orbital periods are related by simple ratios. Under such conditions, gravitational influence becomes periodic and reinforced. Resonances may stabilize a system, locking orbital relationships into long-term patterns. In other cases, they may amplify perturbations and contribute to instability. Observing resonant configurations provides valuable insight into a system's past interactions. Many exoplanetary systems exhibit high orbital eccentricities. In our solar system, such elongated orbits are relatively rare, which once encouraged the assumption that low eccentricity was typical. Exoplanet observations have shown that this assumption is not universal. Elevated eccentricities may result from gravitational interactions among planets or from external influences, such as passing stars. Yet determining the precise cause in each case is often impossible. Another important factor in dynamical evolution is the potential presence of additional, unseen bodies. Even relatively small objects can influence the orbits of detected planets over long timescales. This means that the observed configuration may represent only part of a more complex structure. Science accounts for this possibility, though direct confirmation of hidden components is not always feasible. The dynamical history of exoplanetary systems is closely linked to orbital stability. Not every configuration can persist for billions of years. Numerical simulations show that many initial states lead to rearrangements, including close encounters, planetary ejections, or even planetary engulfment by the star. The systems we observe today are those that have either remained stable or passed through unstable phases and settled into new equilibria. Instability does not necessarily imply sudden catastrophe. In many cases, changes occur slowly, accumulating over immense timescales. To an external observer, a system may appear stable, while dynamically it is undergoing gradual drift. This highlights the importance of timescale in interpreting orbital parameters. Orbital dynamics also influence planetary conditions themselves. Variations in orbital distance and shape affect a planet's energy balance. These changes may influence atmospheric structure and internal processes. Yet the connection between dynamics and physical conditions is complex and mediated by many variables. Science does not yet possess a complete framework to describe these links in a definitive way. The study of orbital evolution combines observation and modeling. Observations provide present-day parameters. Models explore the possible pathways that led there. Such reconstructions are rarely unique. Different scenarios may produce similar outcomes. Conclusions are therefore expressed in terms of probabilities and allowable ranges. Alternative perspectives exist regarding the relative importance of various mechanisms. Some models emphasize early disk interactions. Others focus on later gravitational rearrangements. Current understanding suggests that both processes may be real, manifesting under different initial conditions. There is no universal scenario applicable to all systems. Orbital dynamics reveal planetary architectures, not as static designs, but as the result of long, intricate histories. And as we reflect on these distant gravitational dances, it becomes possible to feel a quiet sense of scale. Worlds shifting slowly over millions of years. Orbits adjusting by fractions, yet reshaping entire systems. Balance emerging from motion. In this calm recognition, science does not rush toward final answers. It listens, it models, it revises. And in that steady rhythm, our understanding deepens gently, patiently, like distant planets tracing their silent paths around their stars. The observed configuration of a planetary system represents only a temporary phase in its long evolution. Even if a system appears stable today, this does not imply that its parameters remain unchanged on cosmic timescales. Recognizing this allows us to see exoplanets not as static objects, but as elements within dynamic, continuously evolving systems. Thus, the study of orbital dynamics and long-term evolution reveals the deeper processes shaping planetary diversity. These processes include migration, resonances, instabilities, and prolonged gravitational interaction. Their analysis requires a calm and measured approach, one that integrates observational evidence while acknowledging the inevitable uncertainties involved in reconstructing a distant cosmic past. Now we gently shift our attention from motion to environment, the conditions on the surface of an exoplanet, if such a surface exists in a familiar physical sense, are determined by a combination of many interacting factors. Temperature regimes, energy distribution, and the long-term stability of these conditions arise not from a single parameter, but from the interplay between orbital dynamics, stellar properties, and the planet's own physical characteristics. In exoplanet science, such questions are approached with caution, because in the overwhelming majority of cases, we have no direct observations of a planetary surface. The primary energy source for an exoplanet is the radiation of its host star. The amount of incoming energy depends on distance from the star and the star's luminosity. Yet even with the same average level of irradiation, real conditions may differ substantially. Orbital shape, axial tilt, and rotational period influence how energy is distributed across the planet's surface and through time. These parameters are rarely known directly, introducing significant uncertainty into estimates of surface conditions. Temperature itself is not something we measure directly for most exoplanets. These models account for reflectivity, the possible presence of an atmosphere, and its properties. For this reason, science works with ranges rather than precise values. If an atmosphere is present, it plays a particularly important role. An atmosphere can redistribute energy, smoothing temperature contrasts between illuminated and shadowed hemispheres. In the absence of an atmosphere, yet the degree of redistribution depends on atmospheric composition, density, and circulation patterns. These parameters are often unknown or only approximately constrained. In such systems, conditions may change dramatically with time, even if average values remain moderate. This reminds us that stability cannot be reduced to a single parameter, such as distance from the star. Orbital stability and evolutionary history matter as well. Even if current parameters allow for a particular temperature regime, this does not mean such conditions persisted in the past or will endure in the future. Stellar evolution, gradual orbital shifts, and atmospheric processes may produce slow but irreversible changes. Scientific analysis in this context focuses on timescales, not snapshots. It is also important to note that the term surface does not apply to all exoplanets. Many discovered worlds are gaseous or possess deep, dense envelopes where the boundary between atmosphere and surface is not clearly defined. This broadens our understanding of possible planetary states and complicates interpretation. Exoplanet science also considers internal energy sources. Radioactive decay, residual heat from formation, and tidal effects may contribute to the planet's energy balance. Internal energy sources are therefore treated as plausible, but often unquantified factors. Stability, in physical terms, does not imply immutability. A stable system is one that can maintain its characteristics in response to small perturbations. Exoplanetary systems may occupy states where minor changes do not produce abrupt transitions. However, if certain thresholds are crossed, qualitative transformations may occur. Identifying these thresholds remains a task of theoretical modeling. In scientific literature, the concept of ranges, rather than single-point values, is widely used. This reflects an understanding that exoplanetary systems possess many degrees of freedom. Observations define allowable regions in parameter space, within which multiple scenarios may unfold. Such an approach avoids overgeneralization and maintains interpretive neutrality. We must also remember that exoplanets exist within diverse stellar environments. Stellar properties, spectral distribution, magnetic activity, evolutionary stage strongly influence planetary energy conditions. Even with identical luminosity, differences in spectral composition may produce distinct atmospheric and surface outcomes. There is no universal template. Exoplanet research is gradually shifting from isolated parameter estimates toward integrated models of planetary conditions. These models incorporate orbital dynamics, atmospheric behavior, and energy balance. Yet their results depend on assumptions and data quality. Science treats these models as tools for exploring possible states, not as precise portraits of specific worlds. Thus, conditions on exoplanets arise from a complex combination of factors shaping temperature, energy distribution, and long-term stability. Observations constrain these parameters only partially. A calm and balanced analysis underscores that science possesses approximate representations, not complete descriptions, of exoplanet surface environments. And the domain of uncertainty remains substantial and, in many respects, fundamentally unavoidable at the present stage of research. Now we turn to another profound dimension: chemical composition. The chemical makeup of exoplanetary environments is one of the key sources of information about the processes of planetary formation and evolution. Unlike orbital parameters or mass, chemical characteristics are not determined directly by dynamics. They reflect instead the history of material from which the planet formed, and the conditions under which that material evolved. The study of chemical diversity in exoplanets relies on indirect data and demands careful, step-by-step analysis. At the stage of planetary formation, chemical composition is shaped by the properties of the protoplanetary disk. Temperature, density, and elemental distribution vary with distance from the star. As a result, substances condensing in different regions possess distinct compositions. Planets formed in different zones of the disk begin their existence with differing chemical characteristics. And over time, migration, atmospheric loss, internal differentiation, and stellar influence may further alter that initial chemical identity. Thus, each exoplanet carries within it a subtle record, a memory of where it formed, how it traveled, and what transformations it endured. In this quiet chemistry of distant worlds, science listens carefully, not rushing toward conclusions, not forcing simple analogies, but tracing patterns gently across light years of space and billions of years of time. However, Subsequent evolution can significantly alter this initial chemical inventory. Planetary migration plays an essential role in redistributing chemical properties. If a planet moves from one region of the protoplanetary disk to another, it may accumulate material with a different composition. As a result, planets may form whose chemical characteristics no longer correspond to their present location within the system. Such scenarios complicate interpretation. They require that we consider not only where a planet is now, but the path it has traveled, the thermal environments it crossed, the materials it encountered, the gradual exchanges that reshaped its outer layers. In this sense, chemistry becomes intertwined with motion. The atmospheres of exoplanets are the primary domain of chemical analysis. Through atmospheric spectra, scientists obtain information about the presence of various compounds. Yet the observed chemical signatures reflect not only composition, but also physical conditions within the atmosphere. Temperature, pressure, and vertical structure influence which molecules appear in the spectrum and how strongly they manifest. Therefore, interpretation of chemical data is always linked to model assumptions. It is important to note that the chemical composition of an atmosphere does not necessarily coincide with the composition of the planet as a whole. An atmosphere may be secondary, formed through degassing, volcanic release, impacts, or external processes. In such cases, it reflects not the primordial material of the planet, but the outcome of its evolutionary history. This distinction is fundamental for understanding the origin of observed chemical components. Chemical diversity among exoplanets reveals itself in a wide range of possible states. Some atmospheres are dominated by light elements, while others are enriched in heavier compounds. These differences point to distinct evolutionary pathways and varying interactions with the surrounding environment. Yet quantitative assessment remains challenging, as many parameters are measured with substantial uncertainty. We must also consider that chemical processes in exoplanetary atmospheres often exist in states far from equilibrium. Stellar radiation can drive photochemical reactions, altering composition at different altitudes. Atmospheric mixing transports substances between layers with distinct physical conditions. As a result, the observed composition is dynamic, not a static imprint of planetary properties, but a constantly evolving balance between radiation, chemistry, and circulation. Chemical diversity is also linked to planetary mass and gravity. More massive planets can retain lighter components over long timescales, whereas lower mass objects may gradually lose them. This atmospheric escape can transform composition over time, leading to transitions between different chemical regimes. The rate and extent of such changes depend on many interacting factors and remain active areas of research. Interpreting chemical data for small exoplanets presents particular difficulty. Their atmospheric signals are extremely faint, and the number of possible parameter combinations is large. In such cases, science often limits itself to identifying permissible scenarios rather than offering detailed descriptions. This underscores the probabilistic nature of knowledge in this field. Comparative analysis between planetary systems also relies on chemical information. By comparing the chemical characteristics of different planets, researchers can identify patterns and divergences. However, such comparisons must account for observational limitations and systematic effects. Without careful treatment, there is a risk of attributing physical meaning to differences that arise merely from measurement techniques. It is essential that chemical composition not be interpreted through predetermined expectations. Science avoids evaluative assumptions and seeks instead to describe observed diversity as a natural manifestation of physical and chemical laws under varying conditions. This approach preserves neutrality and openness to new discoveries. Exoplanet research shows that chemical diversity is a natural consequence of material evolution within protoplanetary disks and subsequent planetary processes. It does not require exotic mechanisms beyond known physical principles. Yet the specific pathways through which these principles unfold remain intricate and varied. Thus, Chemical diversity reflects the complex history of planetary formation and transformation. Atmospheres and planetary envelopes are dynamic chemical systems shaped by multiple interacting factors. A calm and careful examination reveals that chemical diversity is not a collection of exceptions, but a natural and expected outcome of physical conditions acting over time. Now we gently approach one of the most discussed and most carefully limited concepts in exoplanet science: habitability. In scientific terms, habitability does not assert the presence of life. It is a working category, an attempt to formalize the range of environmental conditions under which certain physical states of matter may persist. Most approaches to habitability begin with analysis of a planet's energy balance. Researchers consider whether stable states of matter can exist under specific ranges of temperature and pressure. Yet this analysis inevitably simplifies reality. It relies on a limited set of parameters and cannot encompass the full complexity of planetary systems. For this reason, habitability is always treated as conditional and probabilistic. One commonly discussed element is the range of distances from a star within which a planet may receive energy within certain bounds. This range is often used as a guideline, not as a strict boundary. Thus, location within such a range is neither a necessary nor a sufficient condition for stable environmental states. It is important to emphasize that habitability is not a universal property. It depends on a combination of factors, including the evolutionary history of the system. A planet may reside in favorable conditions only briefly before transitioning into a different state. Science therefore considers not isolated moments, but intervals of time and the likelihood that certain conditions persist. Atmospheres play a central role in defining potential boundaries. They regulate energy redistribution, provide shielding from radiation, and shape chemical environments. Yet atmospheres are neither guaranteed nor permanent. They may form, evolve, and gradually lose components. These processes depend on planetary mass, stellar activity, and many parameters that are difficult to constrain for distant worlds. Moreover, the very concept of a surface does not apply to all exoplanets. For many objects, there is no clear boundary between atmosphere and interior layers. In such cases, discussion of surface conditions loses physical meaning. Discussions of habitability are often connected to chemical preconditions. Scientists consider whether complex chemical systems could exist under particular environmental states. Yet chemical diversity among exoplanets shows that similar physical parameters may lead to very different chemical outcomes. Physical permissibility does not guarantee a specific chemical result. Science therefore works with ranges of possibilities, not predetermined scenarios. And it is essential to recognize that the concept of habitability itself emerged within the context of Earth-based experience. In the quiet vastness of planetary diversity, habitability is not a declaration. It is a question, posed gently, framed carefully, and explored with patience across the immeasurable distances of space. It reflects knowledge derived from processes realized within one particular system. Exoplanet research shows that planetary environments may differ from Earth in many parameters while remaining physically stable. This raises the question of whether the criteria we use should be expanded or revised. Yet any revision inevitably confronts the limits of available data. From a scientific standpoint, habitability should be treated as a classificatory tool, not as the ultimate goal of research. Exoplanets are studied first and foremost as physical objects governed by general laws. Habitability is only one possible aspect of their properties. Overemphasizing this aspect can distort priorities and lead to misinterpretation of data. Modern habitability models attempt to incorporate an increasing number of factors: stellar evolution, orbital dynamics, atmospheric change. However, increasing model complexity does not eliminate fundamental uncertainty. Many parameters remain unknown or weakly constrained. Therefore, modeling results must be regarded as explorations of possible scenarios, not as predictions of specific conditions on specific planets. Alternative approaches to defining habitability are also emerging. Some shift attention away from particular substances or temperature ranges, and instead focus on the stability of energy flows and chemical processes. These frameworks remain under development and currently lack strong observational support. Nevertheless, they reflect an effort to move beyond narrow or anthropocentric criteria. Importantly, abandoning rigid definitions does not mean abandoning scientific rigor. On the contrary, acknowledging conceptual limits allows conclusions to be formulated more precisely and prevents unwarranted generalizations. In exoplanet science, this caution is especially necessary, since the data are fragmentary and interpretations rely on multiple assumptions. Thus, the applicability of the concept of habitability is itself a subject of careful analysis. Habitability functions not as a claim about the reality of processes, but as a description of ranges of conditions permitted by physics. A calm and measured consideration of this concept helps avoid sensationalism and keeps attention focused on what science can and cannot responsibly assert about planetary environments beyond the solar system. Exoplanets do not exist in isolation from larger cosmic processes. Their properties and evolution are closely tied to the history of their host stars and to the galactic environment in which those stars formed. Considering exoplanets within this broader context moves us beyond individual systems and toward a more integrated picture of matter across scales. The star is the central element of any planetary system. Its mass, chemical composition, and evolutionary path influence the formation of the protoplanetary disk and the subsequent development of planets. As stellar properties change over time, so too do the radiative and energetic conditions surrounding orbiting worlds. These changes unfold gradually, yet over long timescales, they may lead to qualitatively different planetary states. The chemical composition of a star reflects the galactic environment at the time of its formation. The material from which both star and planets formed is itself the product of earlier generations of stars and of large-scale redistribution of elements within the galaxy. In this sense, exoplanets carry information about the chemical history of their galactic neighborhood. Differences between planetary systems may therefore arise not only from local disk conditions, but also from broader patterns of galactic evolution. Observations suggest that the likelihood of planet formation depends statistically on stellar properties. Yet these relationships are not absolute. They admit exceptions. This underscores that planet formation is a probabilistic process, shaped by universal mechanisms, but sensitive to contingent conditions. The galactic environment influences planetary systems not only chemically. Stellar density, frequency of close encounters, and background radiation levels may affect long-term stability. In denser galactic regions, gravitational perturbations from nearby stars can alter planetary orbits or even remove planets entirely. Such events are rare on short timescales, but over cosmic durations, they may become significant. Galactic evolution also affects the nature of star formation itself. In different epochs of galactic history, the properties of protoplanetary disks may have differed systematically. Planets formed at different times may therefore exhibit systematic differences as well. Current observations only partially reveal such trends, since the accessible sample of exoplanets is limited to certain stellar types and distances. Exoplanetary systems may be viewed as partial archives of stellar evolution. Their orbital architectures, mass distributions, and chemical properties encode traces of past disk interactions and subsequent dynamical processes. Yet this archive is incomplete and noisy. Many historical details have been erased or obscured by later transformations. Science, therefore, works with reconstructions rather than direct records. Exoplanets also provide a laboratory for studying how stellar evolution influences planetary systems across a wide range of conditions. Comparing systems around different types of stars reveals patterns and contrasts. But such comparisons require careful attention to observational biases and selection effects. Without this care, one risks attributing physical meaning to differences produced by sampling. The galactic environment further determines the background flux of radiation and energetic particles that interact with planetary systems. These influences may affect the long-term evolution of atmospheres and surfaces. Quantifying such effects is challenging, since many operate on timescales far exceeding observational windows. Their study remains indirect. In this way, exoplanets are components of a multi-level system in which local processes are intertwined with global ones. Their properties cannot be fully understood by examining a single planet or even a single star system in isolation. A broader structural context must be considered. This approach complicates analysis, but it guards against oversimplification. Scientific models linking exoplanets with stellar and galactic evolution are still developing. They integrate parameters from multiple domains of astronomy. These models do not provide final answers, but they establish interpretive frameworks within which observed diversity can be understood. Uncertainty within these frameworks remains substantial and is recognized as an intrinsic feature of knowledge. A calm view of exoplanets in their galactic context reveals them not as exceptional anomalies, but as natural expressions of cosmic evolution. They emerge, transform, and sometimes disappear within processes spanning immense scales of time and space. Exoplanets thus become a bridge, connecting the physics of individual stars with the broader dynamics of galaxies. Their study expands our understanding of how matter evolves across interconnected levels of structure. And within this larger perspective, exoplanet science appears not as an isolated discipline, but as part of a wider narrative, one in which local systems and galactic history are inseparably woven together. As we gently bring this long reflection on exoplanets to a close, it becomes necessary to turn toward a quieter question, the question of the limits of knowledge and of how understanding itself is formed in this field. Exoplanet science develops under fundamental constraints. These constraints arise from the impossibility of directly observing most of the processes we wish to understand. They are not temporary technical obstacles that will simply disappear with better instruments. They reflect the very nature of distant cosmic objects. The primary limitation is distance. Exoplanets lie so far away that the only information available to us arrives through radiation, light that has traveled across immense stretches of space. This light carries information about the system as a whole, but it does not neatly separate the planet's contribution from that of its star. To distinguish between them, scientists must rely on models and assumptions. Even in the most favorable cases, we do not observe the planet itself in a direct and tangible sense. We observe the combined effect of its presence. This means that knowledge of exoplanets is always mediated. It always requires interpretation. These models are built on well-tested physical laws. They are not arbitrary. Many parameters are either unknown or only loosely constrained. Different models can often explain the same observational data equally well, while proposing different underlying physical realities. Instead, it preserves a range of permissible scenarios. Another characteristic of exoplanet science is the statistical nature of its conclusions. Most statements apply not to individual planets, but to populations. When scientists speak of what is typical, they refer to distributions and probabilities. This difference between the individual and the statistical is normal. It is expected. It is also important to emphasize that detecting an exoplanet does not mean fully understanding it. In most cases, only a few parameters are known with relative confidence: mass, radius, orbital period. Other characteristics are inferred indirectly and depend on assumptions. Even seemingly fundamental properties, such as the presence of an atmosphere or a solid surface, often remain uncertain. This requires restraint in language and caution in formulation. The limits of knowledge appear not only in space, but in time. We observe exoplanets at a single moment in their evolution, yet their histories span billions of years. Reconstructing that history is possible only through models and analogies. Different evolutionary pathways may lead to similar present-day configurations. Therefore, the past of an exoplanet can rarely be reconstructed unambiguously. Science works with possible narratives, not with precise chronicles. There are also limitations in language itself. Terms such as Earth-like, habitable zone, or even atmosphere are simplifications. They serve as tools for orientation and classification. They do not capture the full complexity of real planetary systems. The development of exoplanet science is accompanied by continuous revision. New data frequently require refinement or even replacement of earlier models. This is not a sign of instability. It is a sign of the scientific method functioning properly. Hypotheses are tested, adjusted, and sometimes reconsidered as evidence accumulates. In this sense, exoplanets provide a particularly clear example of science as a dynamic process. There are also fundamental limits related to the impossibility of experimental intervention. Exoplanets cannot be manipulated. We cannot alter conditions, repeat experiments, or directly probe their environments. All conclusions are based on passive observation and comparison. It's science alongside other branches of astrophysics, where knowledge emerges through interpretation of natural experiments conducted by the universe itself. It is essential to distinguish between what science can assert confidently and what remains hypothetical. The existence of exoplanets and their vast diversity is firmly established. The general principles of their formation and evolution are well described at a broad level, but the detailed properties of specific worlds often remain uncertain. Scientific honesty lies in clearly marking this boundary. Exoplanets also demonstrate that expanding knowledge does not necessarily simplify our picture of reality. On the contrary, as data accumulate, diversity increases. Patterns become richer and more intricate. This requires letting go of the desire for universal, overly simple schemes and accepting complexity as an inherent feature of the cosmos. In this way, exoplanet science teaches us to see uncertainty not as a flaw, but as a characteristic of the world we are studying. A calm reflection on exoplanets reveals them not as sensational mysteries demanding immediate answers, but as elements of a vast cosmic process. They obey the same physical laws as the planets of our solar system, yet they realize those laws under different initial conditions, different histories, different environments. Our knowledge of them forms gradually through the interplay of observation, modeling, revision, and patience. It will always remain incomplete, and it is precisely in this incompleteness that its scientific value resides. Thus, exoplanets represent a domain where the limits of knowledge are especially visible. They show how science engages with distant and inaccessible objects. It is to approach it properly. Exoplanets are not riddles to be solved in haste. They are a field for long, steady, attentive study, conducted at a pace that reflects the scale and rhythm of the cosmos itself. And perhaps, as you rest and let these thoughts drift softly through your mind, you can feel that quiet rhythm, a reminder that understanding, like the universe, unfolds slowly, layer by layer, in patient and measured time.